Hi, everybody. So this talk is about scaling your Kafka pipelines can sometimes be a pain, but it doesn't always have to be like that. I want to start off with a feature of data. Data is really like cheese. If you wait too long, your cheese will spoil. The same thing with data. Data usually has a retention period. If you wait too long to process it, you may end up losing it. And if you have an outage and you have a slow recovery, this is practically a ticking time bomb. So let's talk about Kafka. We love Kafka. It's in the heart of all our systems. But I want to tell you a true story. This is a true story. The events described in this talk took place at Nielsen Marketing Cloud in 2020. September 24, 2020, 5:55 p.m. I get an emergency call from my boss and he says, check Slack. I go to Slack and I see Mayday, Mayday. Earlier today, the zookeepers crashed. And when everything started again, it caused the Kafka instances 01 and 02 to purge their own data. Please add whoever is relevant. This is an outage we had to deal with. The consequences of that day were about 1 day of downtime. We had data loss. We had 5 lost working days that were lost just to resolve it. We had unpleasant customer calls and about $300 in estimates in damages that I estimate. So in this talk, we're going to go over some pros and cons of Kafka. We'll talk about scaling up, scaling down, and how you can improve your Kafka stream pipeline. We'll talk about a few things that could go wrong, and then go into some insights and tactics of how to resolve things that hopefully you can take into your own projects. Before we go on, I want to present ourselves. My name is Opher Dubrovsky. I'm a director of big data engineering at Nielsen. And with me is Ido Nadler, a big data team lead. We love data. We deal with data pipelines, Kafka, serverless, and Spark. And we love it all. Nielsen Marketing Cloud builds marketing audiences and device graphs. And that data is very useful for our customers who are marketers for running campaigns and making business decisions. Just to explain what audiences are basically lists of user device IDs with some label. So for example, pizza lovers or people who are into running and cycling. And each of these groups has a number of IDs that we have associated with, and they are very useful for marketers. Marketers love these. They can slice and dice and intersect those groups and then use them to run marketing campaigns against them. So for example, if there's some cycling event going on in my area and I'm a pizzeria chain, perhaps I want to run a campaign to all the cycling enthusiasts who like pizza and send them some coupon. Great and useful. Some technical details about us. We're cloud native. We run on AWS. We ingest about 60 terabytes of data and store about 5 petabytes in total. We're heavy users of Spark and of serverless Lambda functions. In terms of our Kafka pipeline, we process on a normal day about 25 billion events per day, which is about 300,000 events per second. But at the peak, we processed 5 million events per second. And in terms, if you look at the size of it in terabytes, it's about 200 terabytes a day, 2.5 gigabytes of data per second, and peak, we had about 5.3 gigabytes per second. If you look at our Kafka cluster, it's split throughout 40 different topics and about 9,000 partitions. We have 60 brokers in that cluster, which equates roughly to instances. And the total cost of it is about $540,000 a year. In a nutshell, I want to say a few words about Kafka for people who are less familiar with it. So Kafka is basically a pub-sub messaging system. On the left here, we have producers that produce data, and they send that data in messages to Kafka. Messages are equal to events, basically. And on the right, we have consumers that can consume that data. Kafka is really awesome. It's distributed. You can add more machines to increase the scale. So it's very scalable, it's highly available, and it's fault tolerant. If you dive into the data structure inside, data is divided into topics. Topics are just pieces of information that of the same type. So we could divide one topic for audiences and another one for data on some machines and so forth. And in the topic, we can divide it into partitions for convenience of reading this data. So the partitions could be of smaller size, easier to manage and handle. And our consumers basically would read from all of these topics and partitions, and this is what makes it useful. So I mentioned we love Kafka. Why we love Kafka? It's just an awesome system. It's optimized for high throughput. It has data retention built in, which means it'll delete all data on its own without us having to do anything. It supports multiple consumers. It acts as a great buffer between the different systems and producers of data and consumers. And another nice feature, it allows for reprocessing, which is very convenient. So it's really awesome. But there are a few issues with it. So one of them is processing bursts. The number of consumers that we have to process bursts or to process data at all is limited. We can grow the number of consumers, but it's limited to the number of partitions. So it's a bottleneck. So for example, in this example in front of me, I have 3 topics. I can have 1 consumer reading from all of them. And if I have more data, I can scale it up all the way to 3 consumers, but I can't go beyond the number of partitions. So we're stuck in this situation with 3. And if you calculate the throughput, that means that the max throughput is basically the number of partitions times the consumer throughput. So the max throughput is a glass ceiling that's actually limited by our partitions. Another issue is over provisioning. So overall data is moody and it goes up and down over the day. And we really are consumers, and Kafka for all purposes are in many cases static. That means that we have to over provision it for the times that we have more data. And then during those low times, we end up paying for resources we don't really need. They're not really working very hard during these times. And the third issue is over provisioning. Basically, if we need longer retention on the data, we need more disk space. So for example, if we have one high throughput holiday season a year, we need to provision our cluster for that. And then usually what it means is that we're stuck with that higher provision cluster that's more expensive. Moreover, there's also the data skew issue. So data could be skewed over the partitions, meaning not divided equally throughout the partitions. And then our consumers reading from the partitions may have different loads of work. So some of them may actually have a high throughput and pretty much up to their limits, but some of them may be kind of sluggish and idling away, wasting our money. Let's look at the system we used to read from Kafka. So our old system had Spark as a consumer for the different topics. We had multiple clusters of Spark for the different topics, and they were using Spark streaming to read data from Kafka and store that data in our data lake on S3. The data was coming in as a stream, and Spark was using windows of 6 minutes to read the data and save it. During the low hours, we had less data, so we ended up with small files because the data was divided throughout so many partitions. Each one had just a low amount of data, not a lot of files, so we ended up with small files. If we wanted to correct this in our Spark cluster, that requires repartitioning the data and shuffling the data throughout the cluster. So that added cost and complexity and usually required larger or bigger instances for that cluster, which equates to cost. In addition, scaling up was limited. So if we wanted to scale up, if we had more data, we had a hard time scaling up. We could not scale up beyond the number of partitions that we had, as I mentioned. And reality actually hit us quite a few times, especially with processing bottlenecks. Let's see an example. So here's an example of an outage that we had. Basically, we had a downtime that started upstream from the cluster. So the producers of the data had a downtime, they stopped sending data, and data was piling up there. This took some time to fix, but when it was restored, suddenly we had a torrent of data coming up, and the amount of data, as you can see on the graph, in Kafka shot up. The recovery process basically started here. As new data started coming in, our cluster is starting processing this data and storing into the data lake. And it concluded right here. During that time, if some of that data's retention timed out, Kafka would automatically delete this data. So this really means if you have an outage that's long enough, you lose data, and here's the amount of data that we lost in some of the outages we had. So basically, this is a case of that bomb exploding and data getting lost. Not a great situation to be in. Moreover, the recovery time was very slow. So in this example, we had 4 hours of an outage, and during that time, data kept accumulating. And then just recovering all this and going back to normal took 7 hours. So as you can see, recovering all the data as new data keeps coming in takes a long time, or at least took a long time with our old system. Why is the recovery so slow? Let's take a look. So this is a Kafka cluster example at normal times. We have some data in the partitions and the consumers are reading them happily. After an outage, we suddenly have a lot of data, but still the consumers are limited. We can't add more consumers than the partition. So we're pretty much stuck with the IO that we have across all the consumers. And that usually means a slow recovery. Remember that after an outage, you might need to process data maybe 10 times as fast. And usually these consumers can't grow by much. So we really want to scale the pipeline. But how do we do this? So common sense solutions would be to add consumer machines, but that requires adding partitions into Kafka. That's an option. Another option is to move to larger machines. But again, there's a limit to that. We can't keep moving to larger and larger machines. There's no availability, endless availability of larger and larger machines. So there's really no choice but to add more partitions. Let's go back to the partition calculations and see why that is not such a great solution. The normal throughput, as we've seen before, is the consumer's time consumer throughput. And as we've seen, the max throughput is limited to the number of partitions to consumer throughput. So it seems like if we add partitions, that's great. We'll just increase the max throughput. Again, that's great. But that creates all kinds of problems. First, there's implication for the Kafka cluster performance, because now Kafka will manage tens of thousands of open files, and that requires tuning of the Kafka clusters and all kinds of difficulties around that. In addition, if we have a lot of partitions during those low times, we'll end up with small files and we have to deal with them, just as I explained before. And once we go with a lot of partitions, it's really hard to scale down back to less partitions if we don't need them anymore. In addition, if we decide to stay with the low throughput, that costs us as well in retention time. Let's see why. So assume we need 2 days of data retention, but our processing is really slow, like in the example I showed. So if reprocessing 2 days takes 3 days, that means we really need 5 days of data retention in the Kafka cluster. So that's a cluster that's 2.5 times larger than if we just had 2 days in it. If you recall our Kafka cluster, which costs $540,000 a year, adding 2.5 times to its size would cost us around $800,000 a year just for this retention. So this is really, really expensive. What this really means is that if you can re-architect your system for faster burst processing, you can save money by reducing the size of your Kafka cluster. So this is really great, and there's lots of opportunity if you can do this. All right, so going back to our previous Kafka consumers, which were using Spark streaming, let's look at some of the downsides to that architecture. First, you've seen this slide that our data is moody and it goes up over the day, up and down. So during the low times, our Spark cluster was idling and wasting our money. That wasn't great. During burst, the capacity was limited. And as a result, the cluster was underpowered and we had those long queues as you saw in that burst example I showed you. Again, that's not great. And when we went to calculate the efficiency, so the cluster, as I said, was not really working fully during those low hours, the cluster efficiency was only 30%. So from that respect, that was not great either. We decided to go out and re-architect our system. So we set out with a few goals. One, we wanted the whole pipeline to auto scale. And when I say the whole pipeline, I mean Kafka and the consumers. This is the whole pipeline. We wanted this to auto scale. We wanted to be able to do quick burst processing for all these outages that happen once in a while. And you saw why. And also we wanted this to be cheaper as a whole. But then there was a question, how do we actually do this? If we go with the common sense option of just increasing the partitions, that could have worked. We could have run less consumers in normal times, and then when there's a burst, we'll just increase the number of partitions. But as you've seen, this is not a great option because of all of these reasons I mentioned before. So what we really were looking for is we wanted to keep the number of partitions as it is, break the relationship between consumers, and be able to set our Spark cluster free and scale up with more consumers when we needed. We just wanted to add more and more and keep the number of partitions fixed to the optimal size of our data. So to do that, I'm going to call Ido to tell you all about the concept that we've used, and he will tell you all about it right now. Ido?
Thank you, Opher. Now let's go over for the juicy stuff. Okay, so the main idea that came to us was to spread the work across isolated workloads. By doing that, we can break the relationship between Kafka partitions and the number of consumers we use. So if we take a look at our stream of data, we can break it into small chunks of discrete time slots. We chose hours, but you can use any time slot that works for you. Each one of those time slots is a task, and we can leverage Kafka API to consume the data in Kafka between those hours. So we can have a task processing the data between 3 to 4, 4 to 5, 5 to 6, and so forth. In our case, we use Spark. So we were using Spark clusters that each one of those Spark clusters was consuming the data for between the time slots. And when it ends, it terminates. Now, let's see how it looks if we take a look at the hours along the day versus the time it takes to process. So we are processing an hour of data, right? But you can easily see that some of the tasks are shorter than an hour, because there's not much data to process during that time. And some of the tasks are longer than an hour. It's all about the amount of data that got into Kafka during that specific hour. But even if a task takes longer than an hour, that is no longer a bottleneck, right? Because the next task will start when it was scheduled, and it won't need to wait until the previous task ends. Also, when the task ends, we terminate the cluster and we free the resources. So we are now not paying for this idle time. If you think about it, this is very, very similar to how serverless system works. In terms of cluster efficiency, since we're using Spark, there is a small warm-up time that we are not processing any data. But when we start to process the data, we are pretty much around 90% of load. So the total efficiency is around 75% for the system. Of course, if we can shorten the time of the warm-up time, we can get more and we can get closer and closer to the 100% efficiency. Now let's compare it to the previous system. You know this slide, right? You've seen it already. So in this slide, we have all in this previous system, we have all those wasted processing that we didn't need, right? And the efficiency was around 30%. Now, with the new system, when we are paying only for the resources we need, and the efficiency is around 75%, the new system is now 60% cheaper than the previous one. Now let's look at the mechanics and see how it actually works in practice. So we're using Airflow to managing our pipeline, which means that every hour, Airflow spin up a Spark cluster with the details of what it needs to do. Then Spark go to Kafka and consume the data between those hours. It runs some transformation and write the result to S3. When it ends, it terminates and free the resources. We also leveraging EMR auto-scaling mechanism to terminate idle instances in case of data skew. Okay, but we started with bursts and we started with outages. What happens if there is an outage and we need to run for several hours? That's not a problem, right? Because Airflow will just spin up more and more isolated pipelines, and they will work independently and process the whole time period that needs to get processed. Okay, this is our Airflow DAG. This is how it looks. We basically use one pipeline that uses configuration. And in the configuration, we can tell Airflow which topics to consume, what are the time periods, and any other details we need. Okay, let's see the results of this new system. So here you can see this is the transition point. You can see the left side, where we were in the streaming and how we went to batch. So with the streaming, with the left side, when we were running a micro batch every 6 minutes, and in the right side, we were running an hourly batch. Sometimes we might miss the batch because there was a job failing or cluster crashes, but that's okay because the system knows how to automatically recover and heal itself, and after a while it will rerun the missing task and process the missing data. In terms of cost, with the old system, the cost was pretty steady along the time. But when we move to the new system, now the cost change and it varies day by day because the data changed, right? And we got a 60% drop in cost. Okay, this is a very cool slide because what you see here is how you see the data in bytes by the hour that the system processed. And here you can see how much it cost the system, how much it cost us to process that data. What's nice to see how it pretty much correlates. And this is exactly what we were looking for. We were looking for paying only for the resources we need and nothing more. In this topic alone, we started with $400,000 a year, and we are now down to $160 a year. And we're actually processing more data. We started with the presentation with outage handling, right? And you also already saw this slide. So in this slide, as we said, it took us 7 hours to process the outage and to recover from the outage. With the new system, and this is a very similar outage with, it took us only 40 minutes. And the reason for that is because the system automatically launched 4 concurrent isolated clusters, and that what helped us process it so quickly. So in total, we are now 85% faster in terms of recovery. What we also gain here is that we are now able to reduce the retention policy of Kafka from 3 days to 2 days, and by that, save 1/3 of the cost in terms of storage. Here's another outage we had. You can see that we were out for 28 hours. And when we got to the point of recovery and we started the recovery, we had roughly around 6.5 billion events waiting in line. Now here you can see it took us less than 2 hours, to recover from this outage. That's amazing. In terms of cluster utilization, you can see that after we finish with the initialization stage, we're pretty much close to the 90% with CPU. And with the server load distribution, you can also see that we are very, very utilized. The cluster is fully utilized. Okay, so let's summarize what we talked about. We talked about the implications of not scaling up and down. We talked about the options and the challenges of scaling your Kafka pipeline. We've seen an example of the project we've done and how we optimize it and optimize the solution for doing it. And we derived some architecture insights. So the conclusions are that you really want to design and build your system from the beginning and prepare for the worst. You really need to consider the edge cases, right? You really want to split the work into isolated tasks. In terms of stream versus batch, most of people want to go to streaming because they want the data to flow, but you really need to consider batch. It has its own advantages if you not really need real-time data, and you should aim to remove the dependencies, and as we did with the partitions and the consumers. Okay, so I thank you very much, and I'll conclude with that. You can reach us here. Thank you.
All right. Thank you very much for the interesting talk. Always interesting to, always nice to see hardware being utilized more efficiently. We have a question from Discord from Vonchav. Regarding the scaling Kafka pipeline with the new serverless plus Spark batch approach, how would you scale your Kafka cluster? If your Kafka topics have the same number of partitions, the throughput will still be limited by the number of partitions, unless you change the number of partitions dynamically.
So in our case, not really limited. Kafka has a much higher I/O than most of the consumers because Kafka is highly optimized with binary formats and it doesn't do much processing. It just reads the data, saves it to disk, and then and sends it to the consumers when they read. So as a result, Kafka usually can process maybe 10 or 15 times more than the consumers, most of the consumers you may use. We got around the partitions by using the timestamps because you can use the Kafka API to ask for timestamps instead of asking for the offsets and then having to read from one offset to the next. We actually ask the Kafka API, give us all the offsets in each partition from, let's say, 6 o'clock to 7 o'clock, right? So we get the exact, all the messages we need to read, and then we start reading them. Now, as we are doing this, we could start up additional clusters that would at the same time do the same for other hours, like 7 to 8, 8 to 9, and so forth. So as you saw in the example, we can have 4 or 5 clusters running in parallel as consumers and reading from the same Kafka topic and partitions. And I think at our worst case scenario, we had how many? Like
12, 15.
12 it was, I think 12. I think we had 12 clusters at the worst case scenario running in parallel, and Kafka took it, you know, without a hiccup, not an issue at all. So that taught us that Kafka is amazing. You can really process huge amount of data through it, but also the bottleneck a lot of times are the consumers.
Makes sense. So the number of partitions stays the same throughout the just the parallelization of consumption is increasing. Okay. Hopefully that answers the question, or maybe there will be a follow-up. But I remind the audience that Ido and Opher will be available in spatial chat right after the talk. Let's see. All right. Thank you very much again, and let's go offline.
Thank you.
Thank you.
We are offline.
All right, guys. Thanks. That was awesome.
Thank you very much.
Thank you.
See you on Discord, I guess. You know how many people there were attended? Do you have any numbers?
So I see, sorry. Yeah, I see 192 people online,
Nice.
but it's not clear which track they were in.
Total. How many tracks? There are 2 tracks, right?
Two tracks, yes. Well, they are online in Discord, so they might as well just have Discord open in the background. But that's also some of them might be not in Discord, so maybe admins will know for the.
All right. Super. So we're going over to Discord. I guess we'll disconnect from Zoom.
No, you're supposed to go to spatial chat.
Special chat. Sorry.
Yeah.
Should we disconnect from the Zoom talk?
Yeah, please disconnect from the Zoom.
All right. Super. Thank you.
Thank you.